evening everyone. So, the last class we talked about type 2 error, that is beta, right, and how to calculate beta. So, if for a fixed alpha, beta increases or decreases depends on n and also on sigma of the underlying distribution, right. So, and of course alpha and beta are inversely proportional to each other, right. So, we had a good discussion about beta and then we said the way to calculate beta is what you should know about what is a truth, right, underlying truth, and if your truth and your null hypothesis and your alternate hypothesis are so close by, then beta will be naturally high. To reduce beta, the only way is to bring down n for a fixed value of alpha, okay. So, these are some 4 factors came into play, one is the value of n, the other one alpha, beta and your the sigma of the distribution, finally the difference between null and the alternate hypothesis. So, 5 factors were taken into account and that determines your beta value, okay, and 1 minus beta times percentage is nothing but the power of the test, okay. So, that was towards the end, and then we started off talking about mean as one of the population parameters which we want to estimate using sample mean and conduct hypothesis, but more often it is not, the information is not just in the mean, the information is probably in the variance, okay. So, the information probably is in the variance, not in the mean. So, take a simple example like your thumb impressions, what will be the mean value, the average, the spread, not the spread, the if you look at the patterns, whatever scribblings or patterns you get, probably the mean value may not be much different between people, but the spread is definitely different. The moment you look at here or here, the spread is definitely different, right. So, many a times the information is actually in the spread, not just in the mean, okay, and that is why it becomes important to test our hypothesis on the spread rather than on the mean itself, okay. So, that is what we started off with, and as usual if I know the x bar, if I want to give confidence interval for x bar, I need to know the underlying sampling distribution of x bar, which is normal due to CLT and which is t square t distribution if the sample size is less, and of course the underlying population is normal. Same here, we are talking about sampling distribution of S squared or the sample variance, and what did we learn? Sum of squared normal random variables, sum of squared normal random variables follow chi-square distribution, that is all, okay. So, that is what the idea is. So, now the sampling distribution of S squared is chi-squared, under the underlying assumption is the population is normal, okay. If I make that assumption, then I have clearly this idea. So, we have this chi-square equals to n minus 1 S squared by sigma squared, this is with n minus 1 degrees of freedom, and again n minus 1 because x bar is already estimated. So, chi-square equals to n minus 1 S squared by sigma squared. So, it is actually a ratio if you look at, it is not like unlike normal distribution, it is not plus or minus, it is a ratio, right, ratio of sample variance to the population variance is chi-squared, right, whereas in your CLT it is x bar minus mu, that is a subtraction, whereas this is a ratio, the ratio of S squared by sigma squared follows chi-square distribution, okay. So, in other words if I rewrite this, the confidence intervals I can give for sigma squared, we always give confidence intervals for sigma squared. So, that also is a ratio. If you ask why is it a ratio and why not addition or subtraction like x bar, simple, the underlying sample distribution chi-square is a ratio, it is a ratio of sample variance to population variance, that is why the confidence intervals are also both the sides is a ratio. So if you take confidence interval for mu, it is mu equals to x power plus or minus z alpha by 2 into sigma over root n, whereas here we are talking about a ratio. Sigma squared is between n minus 1 s squared by gamma chi squared with alpha by 2 or 1 minus alpha by 1 minus alpha or alpha. Remember, chi square is not a what? Symmetric distribution. So you have to calculate alpha by 2 separately and 1 minus alpha by 2 separately for n minus 1 degrees of freedom. Okay. So that is what this chi square and sampling variance is about. So remember, we talked about copier example, like I got 5 copiers, a person gets 5 copiers and then you had a mean value. Now instead of a mean, the salesman also claims his copiers are more predictable, in that the standard deviation of jams is only 125. In the sample copiers, the sample standard deviation is 157. So he claims that, now let us go back to this example, I think we had, yeah. So this is the example. So the average number of copies between jams, so suppose copiers average 100,000 and the average number of copies which you get it from the sample is 100,987. Okay. So salesman claims are better and offers to leave 5 units for testing, right. So in this case the mean number of copies between jams is 100,000, that is my null hypothesis, and the alternate hypothesis is not equals to or greater than 100,000. He claims it to be better, so mu A is greater than 100,000, we did this. Now we also add the standard deviation 157, right. Now sample standard deviation is 157 and what is his claim? His claim is 125. So what is my null hypothesis? 125, and what is my alternate hypothesis? Not equals to 125. We can again create a test statistic n minus 1. So here 4 degrees of freedom, n minus 1 chi squared, s squared by sigma squared, it is 6.37. So rejection criterion you can give. So you do not reject the null hypothesis in this case, okay, because the moment you see the rejection criterion you will know that it is not, okay. So you based on that you will be able to reject, or you have to have the table to look at it. So I suggest you go through the chi square table, t distribution, how to look at it, including normal distribution. So far so good, shall we move on? So this is about, okay, so this is about chi squared. We have looked at proportions earlier, so proportions is clear.